Hi guys, my name is Nia-Simone, and this is Lab 3. So in this lab, we'll be observing the simulated orbit of a star around a black hole. The system in this experiment is the star and the surrounding element is the black hole. We will find the net force acting on the system by analyzing and decomposing the change of the star's momentum over time. The purpose is to determine the relationship between the components of the net force and the components of momentum in order to find the mass of the black hole. So, of course, we are analyzing the change in momentum of the system, so we're going to employ the momentum principle. The momentum principle can be described as the change in momentum of a system to the amount of interactions with its surroundings. The equation presented here will allow us to solve for the unknown contribution of net force and thus find the mass of the black hole. The momentum principle is the fundamental principle we'll be using. So in this experiment, we know a couple of things already. We know the gravitational constant, which we will use later, and Newton's universal law of gravitation. We know the star's mass. We also know the experiment takes place on one Earth day. Most importantly, we know the seed, which influences the star's trajectory, and it's based on the unique character sequence of my email address. To continue, we need to determine the momentum of the system with the information we are given. Momentum is the product of mass and velocity. We know the star's mass, and we also know the velocity, which is calculated in the code based on Kepler's laws of planetary motion and his orbital models. To truly understand the implications of momentum, though, we need to observe it over the span of the experiment and determine the difference between the initial and final momentums in order to see what the change is. The same can be done to determine the change in velocity. Analyzing the change in momentum over the change in time will be useful in solving for unknowns, such as net force. So net force we're actually going to set equal to dp dt. This is acceptable because manipulating the momentum principle shows us that net force is simply the change in momentum over time. So if net force is equal to dp dt, their components are equal as well. We can find the parallel component as a product of the momentum's unit vector and the magnitude over time. Since the change in momentum is just the sum of its components, simple subtraction can help us find the perpendicular component of net force. We can use the gravitational force equation and rewrite it in terms of the mass of the black hole. Because we determined an equivalence between the net force dp dt and their respective components, we were able to use the net force, which would have otherwise been unknown, in the gravitational force equation as the gravitational force. Thanks to Kepler's model, we know the displacement of the star, we know the mass of the star, and we know the g constant, leaving only the mass of the black hole as an unknown variable. When we run the code, the mass of the black hole is calculated. It's 1.1 times 10 to the 34th kilogram, which is significantly larger than the star, which is 2 times 10 to the 30th kilogram. But we have to question the accuracy of these results based on assumptions made in the experiment. We assume that the net force is not a culmination of forces, but only a single force. This is not necessarily true in the real world. There could be other forces acting on the star's motion that aren't visible to the human eye. Such mass could be dark matter or a cluster of rocks or really anything. We also assume in this experiment that the gravitational pull from the black hole is located at the black hole's origin. In reality, we don't know for sure if the gravitational pull is at the origin because we don't know the mass distribution or the mass composition of the black hole. Computational modeling is limited because it doesn't consider the infinite possibilities that exist in the universe. In this experiment, we consider the change in momentum over time to be numerically equal to the net force, and we respectively equated their components. Are they truly the same? Well, the bigger the change in momentum, the more force you need to apply to get that change in momentum. So, momentum and force aren't inherently the same. In fact, forces cause a change in momentum. The net force may be made up of a variety of different parallel and perpendicular components depending on the amount of interactions in the system. However, when all the force vectors are summed up, respectively, the parallel and perpendicular net force component values should equal their respective dp dt component values. So, what if we had a new black hole of a different mass? Would we see a difference? I argue that we would. The new mass would have a new gravitational force, so we must consider Newton's laws of gravitation on the system. For example, if the hole had a significantly greater mass, the gravitational pull would be greater and the star would travel at a faster speed. It is possible to find a value for the mass of a new black hole that is different from the mass you found for the original one. We would just have to consider new velocities that result from a different gravitational pull. New velocities mean new momentums, which could have a unique influence on the net force. So before solving for mass, we need to consider these changes on the system and apply them to Newton's universal law of gravitation.